Lesson 8.2 is titled Special Right Triangles, and specifically we're going to look at two types of right triangles and some of their properties, just to use as a little shortcut. They're triangles that we come across often, so yeah, they're going to be very helpful in the long run. Especially, again, these are the types of things that pop up a lot of times in standardized tests, your SATs and ACTs, and then further down the road, pretty much every type of math you're going to encounter. Every once in a while you'll come across these special right triangles. So the first one is a 45-45-90 triangle, meaning we've got two 45-degree angles here, and then obviously it's a right triangle. Now there's a couple things that we can conclude from this. We know that if both of these angles are 45, then that means that this is an isosceles triangle, so both of these sides will be congruent. We can see they've labeled them S and S. Now, if you think back to the previous chapter that we just finished, chapter 7, and we were talking about triangle similarity, and one of our postulates was the angle-angle postulate. We said if you know two angles of a triangle, then obviously you can figure out the third angle just by subtracting, and if you have two angles that are the same, then the third angle must also be the same. And if all three angles are the same, then we know that those triangles are similar. Not congruent, but similar. And we said that all similar triangles have proportional sides. So what we're going to look at here is essentially we're going to look at the proportions of triangles that have 45-45-90. So any triangle that has 45-45-90, those triangles are going to have the same proportions, and we're going to figure those out. We're going to take a look at those, and then we can use them for any situation. So think about, having a little cheat sheet in your pocket of a triangle that had certain lengths, and you would be able to use that as a similar triangle to other triangles on a test. That's kind of like what we're doing here. So in a 45-45-90, both legs are going to be congruent. We said that it's isosceles, and the length of the hypotenuse is the square root of 2 times the length of the leg. So then if you take the hypotenuse, we're going to take the square root of 2 times the length of the leg, in this case S. So I like to remember this as saying 1 square root of 2. Right? So take this side, this length, and you multiply by the square root of 2 to get the bigger length. So that one's pretty easy. The other type of special triangle we're going to look at is a 30-60-90 triangle. Again, we've got 30-degree angle, 60-degree angle, 90-degree angle. And within there, we can look at the proportions of the three sides again. It's going to be a little bit different than the previous one, but if we look here, we can see if you label the shortest leg S, then the hypotenuse is twice that. So the hypotenuse is always going to be twice as long as the shortest leg, and it's going to be the square root of 3 times as long. The longer leg is going to be the square root of 3 times as long as the shorter leg. So the length of the hypotenuse is twice the length of the shorter leg, and is root 3 times the length of the shorter leg. And so there are some formulas that we can use. If we're trying to find the hypotenuse, we just double the shorter leg. If we're trying to find the longer leg, we take root 3 times the shorter leg. And so again, in terms of flow and remembering this easily, I always just remember 1 to square root of 3. And it kind of goes nice and in order there. But bear in mind that 1 is the short leg, 2 is the hypotenuse, and then square root of 3 is the shorter leg, or the longer leg in this case. So let's see how this would apply. Here we have a triangle. We can see it's isosceles, 45-45-90, so it's one of our special triangles, and we can see here the sides here are 5 times the square root of 6. Now at this point, we'd be hard pressed to figure out H if we didn't know these proportions. So if we take a look, we know that the hypotenuse is always going to be the square root of 2 times the leg in a 45-45-90 triangle. So we take the length of the leg, 5 root 6, multiply by root 2. That gives us 5 root 12, but then we can simplify root 12. There's a root 4 in there. Square root of 4 is 2. So we get 10 times the square root of 3. So that would be the length of our hypotenuse. Alright, so we're just looking for these special triangles, and then using the proportions that we know to be true to set up our problem. Again, you can think about this as having in your pocket a little cheat sheet that says, these angles are congruent, and these angles are congruent, and this triangle has sides of 1, 1, square root of 2. Right? So we know angle-angle postulate says that these two, or angle-angle theorem says that these two triangles are similar. And so we can look at the ratio. We can set up the ratio from here as 1 to square root of 2. So then the ratio from here should be 1 to square root of 2. So we multiply this by the square root of 2 to get this. It's just much easier, I think, to remember it this way. Again, another one with 45, 45, 90. This time we can see we have the hypotenuse and we're trying to find the legs. So they tell us it's a square playground, 96 feet from corner to corner. To the nearest foot, they want to know how long the side is. So we've got 96. We know that if this is square and this is a diagonal, it's going to bisect those angles. So these angles are going to be congruent. We know that the sides are going to be congruent because it's a square. So we can just take our 45, 45, 90, where we take the square root of 2 times the leg equals the hypotenuse. In this case, though, we're trying to solve for the leg instead of the hypotenuse. So we would have to divide both sides by root 2, get 96 over root 2, and in this case they just get a decimal approximation instead of simplest radical, right? Things get messy when you have a radical in the denominator of a fraction. So approximately 68 feet on each side. Alright, now one with a 30, 60, 90. So here they tell us it's the 30, 60, 90. We can see the angles here, and then they give us the hypotenuse and they leave the other two out. So they want us to find x and y. So first we're going to take a look and find x. And we said in a 30, 60, 90 triangle, the hypotenuse is always twice the shorter leg. So if we take 2 times x, that's our shorter leg, that's going to give us the hypotenuse, which is 4 root 3. So then to solve, we just divide both sides by 2. 4 and 2 simplify, we get 2 root 3. So there's our value for x. The length of the shorter leg is 2 root 3. And as we move on for y, we said that y, right, from the 30, 60, 90 triangle, we take the shorter leg times the square root of 3 to get y. So substitute 2 root 3 in for the shorter leg, because we know now that x is 2 root 3. We multiply root 3 times root 3 just gives us 3, and 2 times 3 is 6. So our longer leg, the length is going to be 6. Alright, quick checks, as always, are for you to work on your own. We've got one more example and then we're out of here. So another 30, 60, 90. In this case, they tell us it's a rhombus, and it has a perimeter of 100 feet and a 60-degree angle, and they want us to find the area of the garden to the nearest foot. So since it's a rhombus, if we remember the definitions of our shapes, a rhombus has to have 4 equal sides, right? So if it has a 100-foot perimeter and each side is equal, we know each side is going to end up being 25, right? 25, 25, 25, 25 to make 100. So we also know that it's a parallelogram, and so looking at the area, right, because that's what they want to find up here, they say find the, that's not what I wanted, there you go, find the area. So since we're looking for area, we need a formula, and we can use base times height, but remember the height needs to be perpendicular to the base. So we need to find this length right here. Well, if our rhombus has a 60-degree angle, and we draw this height, the height's going to be at a 90-degree angle. This is a 60-degree angle. That means that must be 30. There's our 30, 60, 90 triangle. So take the hypotenuse. Hypotenuse is twice the shorter leg. So if we look at 25, divide both sides by 2, we get 12.5 for the shorter leg, so that's for this little piece down here. Now we can take the length of the shorter leg and find our longer leg. So we know that the longer leg is root 3 times the short leg, so 12.5 times root 3 will give us the height, and then we can take that height and plug it into the area formula. Since it's a parallelogram, it's just base times height, so there's our height, and our base is just 25, one of our sides. So we plug those in, multiply, get a decimal approximation, 451, and so on. So when we round this, about 541, not 451, 541 square feet. Alright, that's about it. Again, it's just a couple shortcuts looking at some special right triangles that are always going to be similar to each other. Every 30, 60, 90 triangle is similar. Every 45, 45, 90 triangle is similar. So we can take advantage of those proportions and use those in problem solving.